that's what it's going to look like. And this, let's see, does this work? That's me. I'm still here. So we'll go back to class notes. And here's my markers. Today is, oh man, this is, no, that's not gonna make it. From again. Today is February 19th. That's not going to make it either. So try again. February 19th. Okay. Let's see. What is, hold on. Everybody, whether you participate in these things or not, you should know that this week is ECS week. So week. Yesterday in the quad area, there were a lot of tables where you're supposed to discover the clubs. But these were only ECS clubs. It wasn't the whole university. So that was Tuesday. Discover Clubs Day. I don't know what the events are. There's an event today, but I don't know what it is. Thursday, they have guest faculty come and speak to classes. A dozen classes are selected out to receive a guest faculty person from some high-powered employer. All right, and I don't know what Friday is. So you got to watch the announcements that are usually posted all over the place throughout the computer science building. Your SI instructor, Koa, leads video game design club. So he was out at his table promoting this club all through yesterday. Sometime when you're in Discord, ask him about it. He likes to talk about that club, how it's changed his professional life, actually. Um, when companies recruit employees, recruit, that's probably not spelled right, employees. It's sort of like the United States Marine Corps. You don't have to do 100 push-ups in a minute to get in the Marine Corps. What they look for is a leader, someone who actively does things. It doesn't matter what you're doing. Leadership counts. And being a member of a club satisfies the employer's desire to have employees who will grow and expand to become team leaders. or project directors and stuff. And you sort of detect that if a person who is outgoing in their person in his personality, talks to others, helps beginners, um, that's a sign of leadership. I don't know what other word to use it. So, anyways, engineering and computer science have a dozen different clubs. Some are so new, created within the last year that I don't even know their names. There's clubs even on machine learning and AI and Bitcoin making and what have you. Uh, but it looks good for a future employer. They know you learned all the technology. Now they want to know, are you a potential future leader? Okay. Join a club. Um, we're going to leave that. I have a whole lecture in the past. I've had a whole lecture on how to get yourself interviewed, because the only media for carrying your message to the company is your resume. And so many resumes are rejected because they're commonplace. You want to get in the door to have an interview, then you can tell all about this great stuff you studied in AI class or you studied in algorithms class. But to get in the door, it takes a really cool resume, an outstanding resume. Join. If you want to put on your resume something about leading freshmen to debug their programs or something, join a club. Okay, I'll leave this. That's a whole topic for a whole lecture on another day. Um, Sarah told me yesterday that I had left IEEE numbers without completing the story. I did an incomplete version of it. Well, maybe so, but I can't remember exactly. So she's asked that she's not here in this at this moment, but she's asked that I finish the story, and we'll take the first half of this class meeting to finish the story. Uh, Let me find. I wish I had black. I didn't bring it home. Let me check. Yeah, let's try this. I triple. Okay, push that up so it becomes seen. Let's revisit this. Here it is. Okay, there's a number line. Not like math class where it's infinite in both directions. This one stops someplace. There's a center point labeled 0.0. And there's a special number over here. It doesn't have a nice name. Smallest positive normal number. And over here are normal numbers. Normal. Up until you reach infinity. And after infinity are nans. N-A-N-S. And in here are sub. Sub means inferior or smaller normals. I can't figure it out. Okay. The negative side of the x-axis is a duplicate of the positive side. So if I folded the paper over, they would match. There's a special number here that is largest negative normal number. Okay. And it's a mirror image of that one. You just take this number and put a minus sign in front of it, and you have that one. And so subnormals extend from here to here. Or here are normals. Sorry, this marker has a poorly made felt tip. Normal. And then there's negative infinity.
We can see all the people.
Thanks. I need to keep pushing it up. Yeah. And then there's more nans, negative nans here. So we're going to find this number, both in hex and in decimal. And then we're going to convert a subnormal number between decimal and hex too. So let's begin. Let me get a new clean sheet of paper. And get the page out of this other pile. Pages, those are the best. Okay. Okay, let's take the words itself. Smallest positive normal number. What would that be? Well, the sign bit is 0 because it says positive. And then, how can we? Okay, I haven't told you all the rules yet. Here's the stored exponent. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. And I pause here because if the stored exponent is all zeros, then it is subnormal. That's the defining factor. So this one between my fingers can't be all. I have to remember to move it up. This can't be all zeros. It has to be the smallest number, but not 0. It's a 1. The mantissa is supposed to be as small as possible. It would be all zeros until you reach the 64th bit. Okay. And then, sorry about it. We break this up in 4s. And it reads 0, 0, 1. Stored exponent. And the mantissa is as small as possible. 0, 0, 0, 0, 0. That is it. Sorry. No, not very exciting, but that's what it looks like in hex. It's a real normal number. It's very, very close to 0, and you can perform arithmetic with it. You can put it in XMM registers and multiply it and add it and so on. Now the question is, what does it look like in decimal? So we have to do the algorithm for conversion in reverse order. So we take the stored exponent, in decimal it's 1, minus the bias number, which is negative 1, 0, 2, 2, 3. negative 1023. And what we have is the true exponent, which is negative 1022. Okay. Negative 1022 is not as famous as the bias number, but it comes up from time to time. And some places I've seen it given a name as the base number. Base number. Base in the sense that it's the foundation. All the other normal numbers are built higher than this one. The base number equals negative 1022. Okay, we're going to use it right now. No, give me a second. I keep looking for a black marker. I have tons of markers here, but they're not black. Try different. Okay, so what does it go like? There's a hidden bit, and then there's the mantissa, which is from here to here. Not a zero, times 2 raised to the true exponent. And that's simply 1 times this other factor. Here it is. It is 2 to the negative 1022. That's the number that's often referred to as smallest positive normal number. You can put it in registers and do math with it, and then it all works. Someone will ask sooner or later, what's the point of working with these ultra tiny numbers? That number is ultra close to 0. And I've asked myself that question. I think it comes from science that is working in subatomic particles. Scientists who are working with the molecule size objects, they're measuring the distance between 2 of them. It'll come out a number like that. The second part of Sarah's, yes,
Professor? Yeah, I was gonna say, can you move it out of it?
I'm remembering, just keep asking me. Okay. There's the calculation, how we came up with this one. Okay. All right, let's take a subnormal number and convert it to decimal. So it will look like when these 3 things are zeros, you're in the subnormal territory, and the algorithm for conversion is not quite the same. The hidden 1 bit is now the hidden 0 bit. So we'll see that coming. Let's suppose we had 4 a 6, 8, 1, 2, 3, 4, 0. Move it up so you can see it. Okay. We're starting with that number. We know that it's a subnormal number because of this right here. Okay. So you don't have to compute a stored exponent. The stored exponent is 0. You don't have to compute the true exponent. The true exponent is automatically going to be negative 1022. Okay, but we do have to deal with the mantissa. The mantissa starts here with 4, and the hidden bit is a 0. Then I'm going to write the 4. 0, 1, 0, 0. The A, which is 10. 1, 0, 1, 0. And the 8. And then lots of zeros after that. Okay. And times 2 to the negative 10.2. We're doing the algorithm in backwards order. Well, it looks pretty ugly. We can make it a little bit nicer if we move this point past the last of the ones. That's a move of 9 places. Then it looks like 1, 0, 0, 1, 0, 1, 0, 1 dot. They're all zeros here. So the left side of the expression became larger. If this is fractional part, now it looks like a whole integer. It became larger by a count of 1, 2, 3, 4, 5, 6, 7 digits. If this got larger by 7 digits, this one has to become smaller by 7 digits. That's negative 10.9. Well, we can even do better before we have to bring out electronic equipment. 1, 0, 1 times 2.
You can see it.
Yes, thank you. Looks like here. And we should be able to simplify this one more step. This is 0, 1, 2, 3, 4, 5, 6, 7. 2 to the 7, which is 128. 0, 1, 2, 3, 4. 2 to the 4 is 16. Yeah, 16. 1, 0, 1, 2. 2 to the 2 is 4. And 2 to the 0 is 1. I have to add all these together. 8 and 6 is 14. Plus 4 is 18. Plus 1 is 19. Carry 1. Looks like a 4. Looks like a 1. So the answer is expressed as 149 times 2 to the negative 1029. Okay. Now that's decimal. There's no binary here. That's a good decimal number expressed in exponential form, not scientific exponential form, but just exponential form. And that's as far as we can go by human calculations, and we'll stop there. And again, that's infinitesimally close to 0. I don't know who. There must be some people in the world who work with tiny numbers, but that's where they get their tiny numbers from. Subnormal numbers. Subnormal.
Professor, when you were converting it into binary, did you forget the 6?
Let's see. You're okay with this, are you?
No, I mean the from hex to binary, because I only see 4, 8, A, and 8.
Oh, for a um. Did I forget a 6? Oh, I blew this answer. We got to do it again. I agree with you. I have a error there. Don't do this on a test. The algorithmic steps are correct, but the conversion back here, let's do it right. Here's the starting number. 0, 0, 0, 4, A, 6, 8, 0. Okay, so Mantissa is from here to here. And after we reach the 8, we don't have to do anything more. Hidden bit 0, 4, 0, 1, 0, 0. A, 1, 0, 1, 0. 6, 0, 1, 1, 0. And 8. And dot, 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 dot. Times 2 to the negative 10, 22. That's that base number. Okay. Simplifying. We're going to move the dot after till it passes the last 1. Then that reads 1, 0, 0. 1, 0, 1, 0, 0, 1, 1,
Can you
0,
move that, please?
1, 0. How many places did I move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I better count it here. 4 and 4 and 4 is 12 and 1 more is 13. So this became smaller by 13. 10, 35. Can you read that number? Negative 1035. Okay, it's correct, but I couldn't call this decimal number. It's mixed binary in here. So we want to try and remove that. We could use a calculator, but let's remember the fundamentals here. This is position 2 to the 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the first one is 2 to the 11. I'll count it again. 0, 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 8. 0, 1, 2, 3, 4, 5, 6. 2 to the 6. 0, 1, 2, 3. 2 to the 3. 2 to the 2. And 2 to the 0. This is double 1024, so it's 2048. What is that? That's 256. What is that? That's 64. And 8 and 4 and 1. Kind of like a mess, but let's do it quickly. 8 and 6 is 14, plus 4 is 18, plus 8 is 26, plus 4 is 30, and plus 1 is 1. 3. 3 and 4 is 7, plus 5 is 12, plus 6 is 18. Okay, final answer. 2, 3, 8, 1 times 2 to the negative 10, 35. Okay, got it. That's the technique. I had left out 6 or something when I was back here, but it's all accounted for now. There's an A and there's a 4 and an A and a 6 and an 8. Okay. I think that's, let's see. we'll do one last. Sarah's not here, but she asked that I review these. She said I didn't do it completely the last time. That may be true. Okay, so let's take something in reverse. How about 7 times 2 to the negative 28? 1028. What do? We write a 7. 1, 2, 3, dot, times 1028. 28. The algorithm is somewhat different. Now here it goes. We want to change this. This is a 2. We want to change this expression so this becomes the base number. That means it would have to grow by 6. So it's going to become times 2 to the negative 1022. It became larger, closer to 0 by 6. Therefore, this one has to shrink by 6. So there's equality maintained here. This is good. This is in the standard form for subnormal numbers. Are we ready to write the subnormal number? Okay, let's do it. First in binary, the sign is 0. Okay, I have to write all these bits. There's 11 zeros. 3, 4, 5, 6, 7, 8, 9, 10, 11. Then there's the mantissa part, which is right here. The hidden 0 disappears. 0, 0, 0, 1, 1, 1, 0, 0, and there's lots of zeros after that. Okay, so group this in groups of 4. Here, 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 here. And then we'll be done. 0x. First group, second group, third group, fourth group, fifth group. That's actually a 12, which we write as A. And all of them are zeros after that. Yes, I did it again. A 12 is not A. 10 is A. 12 is C. That's a C. Okay. And then, that looks sloppy writing. I should be able to do better than that. 0. 1, 2, 3, 1. C 0, 0, 0. 0, 0, 0, 0. 0, 0, 0, 0. Okay, I think that time will. I spent too much time here. Okay, I'm gonna change the subject, everybody. Why did we move 6 decimals or step back here? Oh yeah, here's the answer. This is a 2. Here's where we are at first. We're at this place. But the algorithm for subnormal numbers says you cannot have any other exponent except negative 1022. So then you think mathematically, what do I have to do to this expression so that my exponent changes to negative 1022? Well, this is a negative number. So by changing this to 1022, you've actually increased, you've increased, you think negatively. You've moved in the positive direction on the number line. If you subtract 6, will get you to here. Does that make sense, everybody? It's a difference of 6. And the exponent got larger. Therefore, this 111 has to become smaller. And its dot moved from here to here, a corresponding move of 6 places. The exponent changed by 6, larger. This has to change by 6, smaller. And now we got to the next step. Okay. Sullivan, I think we're good to go. I'm changing the subject. Here's my paper. I'm keep losing it. It's behind me. Okay, I'm going to show you macro. Macro is a cousin to a function, at least in the programming sense. A macro is like a function. We use functions. Here's a principal use of functions. It's to subdivide the solution space into pieces that are more manageable. You could do the next assignment in one huge assembly file. Just put it all together, all the pieces in that one assembly file. But as that gets bigger and bigger, it's harder to manage it. So we use functions. I've given you last assignment a calling diagram. This one calls this one. This one calls input array. Input array calls convert something always float. And there's other stuff that happens. That's partitioning the solution into manageable modules. Okay? Functions do that very well, and we use them all the time, but they have an overhead. The cost of calling a function is in computer terms, it's expensive in time to call a function. If driver calls manager, when that happens, the stack is, in other programming languages, the stack is automatically increased from where it was to a new add-on section called an activation record that belongs to this function executing here. So it owns all that space, and in that space are stored the values for all of its variables. So the mere act of calling this function causes this to be created. It causes, it causes the RIP to change to execute this function where it was executing back here. It now has to execute here. And when it terminates, all this stuff here that belongs to function M manager has to disappear. Okay. I'm doing that kind of fast, but I'm pointing out that there's a lot of, they call it overhead. There's a lot of cost in time to call functions. Okay. But functions are very secure. They have separate space to store all their variables. Macros let you partition the space into workable areas, but they don't have extra storage on the stack. You don't compile them and put an extra line in your bash file. You're going to see right now that they're rather simple gadgets, but they still break up the code into pieces that are good for humans. Okay. Let me see. Let's make one right now. You make one.
Move it out, please, sir.
Yes, sir. Yes. Okay, everyone got this back here. Driver calls manager. That causes a whole bunch of a chain reaction that creates more space on the stack. Variables that are being passed, their values are placed in here. The RIP register has to be reset to start executing manager. This piece over here is called activation record. Functions are great. They do the job there of them that is expected, but sometimes you don't need that much power. A macro will do the job also. So here is the code for, we're going to do the macro that computes the area of a rectangle. You say the word macro, and you give it a name. Area rectangle. And then you tell it a single digit, not a single digit, a single integer. How many parameters are going to be needed? For area of a rectangle, you pass to it the length is one, the width is another, and then you pass back the area. That's the third one. So you put a 3 here. It says three numbers are going to be involved here, and I was going to write the quick code for that, but I need to explain. Where's my? I need to one lost paper. We'll get there. Uh, let's. I'll come back and complete this in a moment. How to call a macro. A calling statement in the manager over here would look like this. You give its name, area, rectangle, leave a space, R8, leave a space, R9, leave a space, RDX. Those are the 3 parameters I've chosen. At another place, I could call it with R12, R13, R14. But this is parameter number 1. This is parameter number 2. This is 3. So I should put comments next to this that R8 equals width. R9, that's an 8, equals height. RDX is area. Okay. We humans will forget, but that's how you call it. Then no parentheses, no commas separating anything. You just the name of the macro, and then registers. You can put hard numbers in there, except for the last one. What I mean, it could be this. AREA rectangle, 5, 9, and RDX. Width, height, and a place to return the area. Okay. Assignment 3 asks you to make a couple of macros. Let's finish the one I had started. Make a % sign and the word macro. Leave a space and give it a name. Area rectangle. And then say 3, because there's 3 parameters that are going to be needed. Some are passed in, one is passed out. Okay, so here is what we could do. Inside of here, the three parameters are known as %1, %2, and %3. So I'm going to do this just for good illustration. R12, that's R12, %1. Move R13, %2, multiply R12, R13, multiply width times height, and move R, %3, comma, R12. Okay. We don't know the variable, but it'll be there when at the calling time. So I'm putting the area that was computed here, put a copy back here into the third parameter. Then you close it off and you say and percent in macro, ENDMACRO. And you already saw the program that has access to this is going to call it by different means. Just area rectangle 17, RAX, and R15. Later I can switch these. This one has to be a register because it's going to receive a value. These could be hard numbers like 17 width, and numbers in RAX is 12 height, and then you'll get an answer here. That's what it looks like when you call it. It's a little different than function calls. Function calls would have parentheses around these, and you have to separate them, and you have to match the right types together. Okay, well, what's the clock say? We're just not late and not early. Okay, one more new concept, and then we're done for the day. I'm reaching for paper. Stack of paper still. I got it here. I like the white ones. Now, it's possible to put the definition in the same file with the caller, but it's more convenient to put it in an include file. Okay. So I'm not really going to spend time on placing this at the top of the assembly function that plans to call area rectangle. What we want to do is make an include file. Make a file. We have to give it a name. Named geometry .inc. Okay. In that file, we put the definition of the macro. Okay, I need to move it up so you can see it. There's the macro. We're going to put its definition inside of a file. And so it's here. I don't want to recopy it, but here's the area of rectangle. Okay, it's defined here. Okay, and if you have more to do, you can put other macros in here. And you can line up 3 or 4 of them. And close the file. There's no special marking. Just save the file under that name, the name you've chosen. to have INC for include is common practice. All right, so then in the declaration section of the assembly function is going to call these macros, you do one thing. You have the declaration section at the top. It's not pound sign, it's percent sign. Percent include quote geometry GEOMETR1 dot INC. That's what it looks like. Now the caller function has access to all the macros inside of here. You can just use it directly. Okay. So this goes at the very top. And then in segment text, you can call these macros any place you like, any place you need them. You know what we're going to do. Area rectangle. $22, $17, or $15. How does it know about it? It's because it's been included inside of here, and then the caller function has access to all the macros inside of there. Okay. Am I under? I still don't need a camera. That's what I'm trying to illustrate. We make an outside file. You can name it anything you want. It helps to call it .inc. Put macros. They're usually short, 5 to 6 to 7 lines, as many as you like. Then include it into the, say, the manager function. And manager can call those macros like this. It doesn't create, it's not a function call. It doesn't create extra space on the stack, or you don't have to put an extra line in your bash file. Let me see if we're almost ending. Let me look at, I'll share my screen. See if I put that in the bash file. Do I have that still open? Okay. Oh, still, where is it? Oh, it should. Here's the example. Okay, this is the caller one. You see, there's a call. I made the example on paper. It's this one right here. The area of something using integer data. And there's 1, 2, and 3 parameters. Okay. So what happened in the, oh, here's the ink. I think that's it. What is this? A macro computes the area of a right triangle. Okay. Number of parameters, 3. Here's documentation, so future programmer knows what these stand for. Number 1 parameter is the length of side. Number 2 parameter. Number 3 parameter is the computed area. This is passback. These are all unsigned integers. You do some yeah. And then here it is copying the number that was computed is put into parameter number 3, and the caller of this macro will get an answer in the 3rd parameter. Let's see, I'm still, last thing today, let's look at the bash file. Yeah, let's look at What do we compile? Driver, okay. Assembly function, okay. I don't see, there's nothing about, there's nothing here about the include file. You know, I think, what was the include file's name? It was hypotenuse.inc. Let me go back to that. This is, I don't know what's going to happen here. This is just an experiment. What if I assemble the include file? Will it complain? Let's do it right now. Okay. NASM hyphen FELF 64 and I'll try hyphen L. What was the include? It was called Pythagoras. No, the include file is here. Hypotenuse.inc. HYPOTUSC C dot LIS and HYPOTENUSC dot AS. It's not include. And INC. This is not normal to do, but let's. I wanted to try the experiment, see what happens. Let's save it and go back here. Do I have a terminal window open? Can't hardly see it, but we'll try it anyway. R.sh /r.sh should be okay. I think this is the first side of a triangle. That's okay. I'm not interested in that. I'm wondering what did it do with Pythagoras is missing. Warning, Pythagoras.o is missing. I'll explain that another day. That's not related to this. Okay, Control C. Let's see if it did. That's pretty amazing. I didn't know this, everybody. There's the include file. It actually, NASM actually created a list and an O. I can't believe this. Let's see if we got to do this another day. Pythagoras is the main assembly file. Hypotenuse is here. And it did something with it. It created a hypotenuse list. Okay, that's understandable. Hypotenuse O, it created that. But I never link a hypotenuse O. Sorry, my mouse slips. We'll have to discover this another day. But it works without it. You saw me running it for a minute ago. You don't need this, but it's what I've seen it used for is a syntax checker. If I had errors in the include file, they would show up here. But as far as linking, the machine knows how to take care of that itself. Hypotenuse.o is not down here. All right, everyone. Go to the Discord and pick up a copy of assignment 3. Koa posted it for me earlier this morning, and we'll all gain some experience in making macros. That's it. It's about 11 o'clock. Have a good day, everybody. Thanks for coming. I'm going to stay on Zoom here until about 11:45. And next week, I'll be in the classroom. You're welcome, Hamid. Oh, Kyle in dot data above dot data, but I don't like that style. I want you to put it in a external file. In my example of teaching here, it was called geometry.inc. It's in your assignment 3, I want you to make an external file. Give it any name you like, but put extension INC on it. And then put your macros in there. And then include that file before .data even, higher up than that. It's one of the first things you declare is the include statement. Okay. 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 Well, I'm going to be here. I'm open to questions. You can send them in private chat messages or public chat messages, or if you want, you can ask me things in voice.
I have a question, Professor.
Sure. Yes.
On the past exams that you have posted,
Yeah.
there's questions on the GDE or GDB, sorry.
Yes.
We haven't super covered that much in
No,
class. Is there like a method you have that you recommend for studying them? Is it just in the book or?
it's in the book, but here I have to tell you in advance. The author's chapter, I think it's chapter 6 on GDB, is very incomplete. It's it doesn't do the job well. I like the rest of his book, but the GDB chapter is just it's not good enough. It's okay to read chapter 6, but keep in mind I'm going to do more. In fact, I got to make a point that that's going to be the starting lecture of next week. We're going to go to GDB. You need this. Oh, and how do you study for it? I'm going to show you. GDB is full of hundreds of commands. They're commands that you enter when the program pauses. I'm going to show you a dozen or 2 dozen or 3 dozen of these. The best thing you can do is to make your private personal catalog of each one of those commands. And then when test time comes, it's an open note test, you refer to that rather than
Control F?
referring to, yes.
Okay.
Yeah, you're okay. Just refer
Okay.
to it.
Okay, cool. Thank
Okay,
you.
we'll do it next week.
All right. Thank you. Have a good day.
You're welcome. Thank you.
Hi, Professor.
Yes, I'm listening.
Yeah. I had a question about